functions of two variables. That's to say we're going to have a function f of x and y, and it's going to give us a number z, a unique number z. So that consequently, the graph of such a function is going to have for each pair x, y, one point z, and we will graph then the point x, y, z, and this will result in a surface with one point corresponding to each point x, y in the domain of the function. We've looked at some examples of these by looking at quadratic surfaces. In particular, for example, if we consider f of x and y is equals to, say, x squared plus 2y squared. The graph of this for each number x and y is going to correspond to a point f of x and y. And if we look at the traces in the xz and the yz plane, first of all, I suppose let x equal to 0 here. We now consider z equal to x squared plus 2y squared. And so we've got z is 2y squared, and so that's a parabola opening up like so. When we let y equals to 0, we look at the xz plane, we find that we've got z equals x squared, and so that's a parabola opening like so. And so the resulting graph is going to be that of a paraboloid. All right, and another thing that you want to look at when you're graphing these, besides the traces, right, are called the contours. Right? And here, these are familiar. A contour is a particular level, z equal to a constant intersecting with the function. Sometimes it pays to actually draw a graph of what the contours look like. We'll take a look at that in a moment. Let's take a look at another one that's familiar. Z equals f of x and y is, say, x squared minus 2y squared. Right. When y is equals to 0, we have z equals x squared, and so in the xz plane, what we're looking at is a parabola opening up. When x is equal to 0, we have z equals minus 2y squared, and so what we're looking at there is a parabola opening down. Right. And this, the graph of this is going to be hyperbolic paraboloid. And it's going to look something like this. It's defined for each pair of numbers, x and y. We get a value here, z equal to x squared minus 2y squared. A third example would be that of a plane. Most planes, except for the ones which are vertical, are going to be graphs of functions. So that, for example, if we let z equals to minus 3x plus 2y plus 4, all right? This is a function of x and y. F of x and y given by minus 3x plus 2y plus 4 for each point x and y. There's a number z here, and the graph of this, to graph this, we want to graph this plane. All right? That's to say, when x is equal to 0 and y is equal to 0, z is equal to 4. When, so here's one point on the graph at 0, 0. And then if we look for the traces in the xz and the yz planes, when x is equal to 0, z is 2 y plus 4. Actually, here, let's plot the point here. When x is 0 and z is 0, then y is equal to minus 2. And so this is a point here on this plane. And when z is 0 and y is 0, we've got x is equals to 4/3. So here's another point here on this plane is going to be at 4/3. The resulting plane is going to be formed with this triangle right here. And continue, of course. And it's going to be this plane, and for each point x, y, there's going to be one value z. So here are some examples of functions where we've already looked at the graph of the corresponding equation. We're going to take a look at a method for drawing the graphs of functions of two variables now, which involves what are called contour maps. Let's consider, for an example here, f of x and y equal to z, which is x times y. And suppose we wish to get the graph of this. And let's notice now, if we look for the traces in the xz plane when y is equal to 0, z is equal to 0. So that the entire x-axis is the trace in the xz plane. When x is equal to 0, z is also equal to 0. So the traces are these two axes. That doesn't tell you too much about what this might look like. Let's do the following. Let's draw a two-dimensional coordinate system, x and y. And now, the x-axis and the y-axis represent the 0 contour. That's to say that these are the places where this function is equal to 0. Let's take a look at where it's equal to 1. That's to say, if we have z equals to x times y equals 1. Well, the graph of this is going to look like this. This is 0 here, and so that this is 1. And also over here, this is 1. So those are the 1 levels, right? If we look at where z is equal to 2, let's say when is x times y equal to 2, that's going to be x times y is 2 over here, and also over here. So those are the 2 levels. Right? For the minus 1 levels, z equals to minus 1, or x times y equals to minus 1. Right? Those are going to be these curves here. Let's say it's minus 1 there. X times y is minus 1 there. And it's also minus 1 over here. Minus 2, x times y equal to minus 2. Right? Those are these like so. Right? And having drawn a few of these, now it's clear where the rest of them are. That's to say, the 3 level is up here and down here, the 4 level and so forth. The 1/2 level is down here and over here. The minus 3 level here and here. The minus 1/2 level there and there. Right? So we can get some ideas to what this looks like. That's to say, as you proceed outward here, in this direction, we've got the 1 level. That's to say, this is up at the 1 level out here. And then the 2 level. And likewise, the 1 level is back here. And the minus levels are over here. That suggests that maybe this thing looks like a saddle that's been turned. And that turns out to be the case. And we can see that by looking at the graph of when x is equal to y, in which case we get z is equal to x squared. Right? So along the line x equals y, the graph of this looks like z equals x squared, or like so, and so forth. when x equals minus y, z is equal to, on the graph on the line x equals minus y, we have z equals minus x squared. That's a parabola opening downward like this. Along this line here, huh? So you expect something like this for the resulting graph. Namely, it looks like a saddle shape here and here. So that the graph looks something like this. Where the saddle's been turned 45 degrees. And this coincides with the picture that we got from the contours, namely, the one contours are up in the positive quadrant for x, y, and the third quadrant, the first and the third quadrant, those are positive. Right? Positive and positive here. Right? The negative ones are in the second and fourth quadrants. Huh? So back here, the saddle is negative. Over here and over here, the saddle is negative. Okay. In general here, this is actually a familiar idea. That's to say, there are contour maps of terrains are drawn, for example, where this might be, let's say, the 10 level, and this the 9, and all the way down here to where, for example, this might be the 1 level, right? When we're talking perhaps miles above sea level, right? The 0 level might look like so, right? There might be a -1 level, and the resultant picture of this object is that it's going to be some sort of a mountain here, right? With these various levels. Right? So drawing the contour map allows you to get a picture and visualize what the graph looks like. And here's an example of a numerical example where this is actually done. We want to look now at the analogs, and we'll be doing this for some time, the analogs of the concepts for functions of one variable, for functions of two or more variables. We'll frequently be looking at functions of two variables and keeping an eye on functions of three or more variables. The problem, of course, with functions of three variables is that their graph would have to be in a 4 or higher dimensional space, and so it's not going to be possible to draw a graph of such a function in any way, any easy way at any rate. We're going to talk about the limit of a function of two variables, f of x and y, as x and y approach a point x naught, y naught. The idea here is like this. We've got this function up here, f of x and y, take a particular point x naught, y naught, and we want to know what the limit is as you'll consider points x, y close to x naught, y naught. Is there a limit, and what is this? Well, the definition of this is going to be analogous to that for functions of one variable. Let's just say this is going to be equals to L if you reach epsilon greater than 0, there is a delta greater than 0, so that the distance from f of x and y to L, that's to say absolute f of x and y minus L, is less than epsilon when 0 is less than the distance, when 0 is less than the distance from x naught, y naught to xy. That's to say, and is less than delta. That's to say, xy is supposed to be close to x naught, y naught. We could write this in terms of the distance by writing that this is when 0 is less than the square root x minus x naught squared plus y minus y naught squared is less than delta. So, one way or the other here. Right? That's to say that if we take points x, y, close to x naught, y naught, the values of f and x and y should be close to the number L. Right? Now, it doesn't matter whether the function is defined at x naught, y naught or not. We don't consider points x, y, where x, y is x naught, y naught. 0 is larger than this. This distance is larger than 0, so we don't consider points x naught, y naught. But if we wish to consider such a point, right, then what we're going to be talking about is whether or not the function is continuous. That's to say, we'll say that f of x and y is continuous at x naught, y naught at this point if the limit as xy approaches x naught, y naught of f of x and y is the value of the function at the point x naught, y naught, f of x naught, y naught. Now, for most functions that you construct using algebra, you're going to have this type of continuity. Right? We're going to want these exact same definitions here for functions of 3 variables. That's to say, the limit as x, y, z approaches x naught, y naught, z naught of f of x, y, z, right, will be defined to be L if for each epsilon greater than 0 there's a delta, so that the distance from the difference between f of x, y, z and L is less than epsilon when the distance from x, y, z to x naught, y naught, z naught, abbreviating this like this, distance between this point and this point, when that's less than delta, then this will be less than epsilon. So this is going to be L if for each epsilon greater than 0, there is such a delta greater than 0, so that this happens. Right? Now, as I mentioned, graphing functions of 3 variables is not particularly easy. However, there's one thing that you can do with 3 variables, and that is you can draw a contour map sometimes if the contours are relatively simple, or you can draw a group of contour maps to see what's happening. Take a look at a simple example of that. We looked at f of x, y, z equals to, let's say, x squared plus y squared plus z squared. Then the origin would be the 0 contour. Right? The sphere of radius 1 would be the 1 contour. Right? The sphere of radius 2 would be the 4 contour. So this is where this function is equal to 4. The function is never negative, and so you can get a sense for how this function is growing. You can think of the function as assigning to each point in 3-dimensional space a real number. Right? And it's 0 at the origin, it's 1 on the surface of this sphere, it's 4 on the surface of the sphere of size 2, 9 on that of size 3, and so forth, of radius 3. Yeah? Right? So, we will use this definition for functions of more than 2 variables. However, the picture is easiest to draw for functions of 2 variables where the graph occurs in 3-dimensional space. There are several analogs to differentiation in higher dimensional spaces, in two-dimensional space for that matter. And we'll be looking at some of those. The first is a sort of an incomplete notion here, and it's called partial derivatives. So given a function f of x and y, so given this, right, we want to define the partial derivatives of f with respect to x and with respect to y. The picture is something like this. Right? We've got this function f of x and y here. Right? We wish to look at a point x naught, y naught, let's say, and fix y naught and consider x varying in this direction. Well, in that event, what we end up with is some sort of a curve up here, and what we want to know is what's the partial with respect to x, so what's the derivative with respect to x along this curve as you head in the positive x direction here, right? So, given this, we're going to want to compute that derivative, and the notation for the derivative is f sub x at x and y, or sometimes it's written as a sort of an upside down roll, or and of f with respect to x. This is read the partial derivative of f with respect to x, and it's always considered to be at the point x, y if there's no parentheses there. So given a function f of x and y, we want to define this, and this is the definition. The partial with respect to x at some point x naught, y naught is going to be equals to the limit as h approaches 0 of f of x naught plus h and y naught minus f of x naught and y naught divided by h. So what this means is you fix y naught and you look at the difference quotients for that fixed y naught, f of x naught plus h minus f of x naught and y naught, divide by h. This is the same as the ordinary derivative if y naught is fixed. Right? And now, of course, if this exists for each point x naught and y naught, it defines a function of x and y. The partial with respect to y and x naught, y naught is equal to the limit as k approaches 0, f of x naught, y naught plus k, minus f of x naught and y naught divided by k. So that's achieved by fixing x naught, looking at this curve here along the surface. As y proceeds from the left to the right, and computing the slopes of the secant lines and taking the limits, huh? So that this slope here is going to give you the slope of the tangent line in this plane of f of x and y. Okay. Similar definitions for three variables, except there you have got partial with respect to x at x naught, y naught, z naught, partial with respect to y at a point x naught, y naught, z naught, and a partial with respect to z at x naught, y naught, z naught. Right. I want to look at a little bit of a bizarre function right here, because even if the partial derivatives of a function exist at every point, it's not necessary that the function be continuous. I want to consider the function f of x and y equals to 2xy over x squared plus y squared, and I want f of 0, 0 to be equal to 0. So this is going to define this function here, and I want to take a look at the graph of it. Right. Notice that the partials here all exist, and you can compute these partials at a point x, y as follows. Fix x and differentiate with respect to y. Treat x as if it were a constant and differentiate with respect to y. So that the partial with respect to x here, for example, at a point x, y, is going to be given by fixing x, differentiate with respect to y. So we get the denominator, x squared plus y squared, times the derivative of the numerator, fixing x, differentiating, or fixing y, differentiating with respect to x. So that's going to be 2 times 2y minus the numerator, 2xy, times the derivative of the denominator with respect to x, fixing y. So the derivative is x squared is 2x, and the derivative of y is 0. So we get times 2x over the denominator squared. Right. Similarly, you can compute the partial with respect to y at any point x and y. Right. Fixing y and differentiating, or fixing x and differentiating with respect to y here, we're going to get that this is equals to the denominator, x squared plus y squared, times the derivative of the numerator, with respect to y now, treating x as a constant, so this is going to be times 2x, minus the numerator, it's 2xy, times the derivative of the denominator, which is, with respect to y, is 2y, derivative with respect to y of x squared, if x is fixed, is 0, so this is times 2y, over the denominator squared, x squared plus y squared quantity squared. So at every point here, this, as long as we're not looking at 0, 0, this has got a partial derivative, and at 0, 0 you can notice that part of the graph of this function consists of the axes. That's to say, if x is equal to 0 or y is equals to 0, then z is equals to 0 here, where z is f of x and y. And so the two axes, the x-axis and the y-axis, are on the graph of this function. Now the function looks a little bit strange. So it looks like a stingray. That's to say, okay, this function's got partial derivatives at every point. The partial derivative at 0 is equal to 0, both the partial with respect to x and the partial with respect to y. But what does the function look like? Well, if we let x equal y in this expression here, we find that we're looking at 2x squared over 2x squared. Right? This is when x is equal to y. This looks like 2x squared over 2x squared. So consequently, above the line y equals x, the function is 1. Right? Likewise, if we let x equal to minus y, then we have then what we have is minus 2x squared over 2x squared, or minus 1. So the graph of the function along the line y equals minus x is minus 1. So the function is down over here, like so. Well, if you look at various other lines going through the origin, what you find is that this function comes up like so and increases to 1, or perhaps like this, increases till it gets to 1, and then gently decreases until it gets to 0 over here, and continues to decrease over here until it gets to minus 1, right? And goes on over here like so, so that on the y-axis it's 0. Continuing this around, it's plus 1 over here, right? and then it goes down to 0 here. It continues and goes down to -1 here, and back up to 0. So something like that. Sort of looks like a stingray here. It's 1 unit high here, and back it's low by a unit in these two quadrants. Right? Its partial derivatives exist, and they exist at 0, but this function is clearly not continuous, because continuity means it's not continuous at 0, because continuity means that if we stay close to 0 here, this function has got to get close to its function value, and it doesn't, because it's 1 over here, it's -1 over here. So the partial derivatives of a function can exist, even though the function is not continuous. However, let me repeat that. Most of the functions that we look at will be continuous at the points in their domain. Let's take a look now at some functions of 2 variables and 1 of 3 variables, say, and notice that it's really very simple to take the partial derivatives. Once you get the knack of it, it's as simple as differentiation. Let's suppose we look at f of xy equals to x squared y plus 3x cubed y minus 4x. Okay, this is a function of x and y. Let's compute its partial derivatives. The partial with respect to x at x and y. To compute this, we treat y as if it were a constant and differentiate with respect to x. So we're going to get that this is equal to y times the derivative of x squared, or 2xy, plus y times the derivative of 3x cubed, that's 9x squared y. Treating y as a constant differentiating with respect to x, we get that this is -4. The partial with respect to y of this function. Right? Here we treat x as if it were a constant and differentiate with respect to y. So the derivative of this with respect to y is going to be x squared times the derivative of y with respect to y, which is 1, plus 3x cubed. The derivative of y with respect to y is 1 again. And the derivative of 4x with respect to y is 0. It's treated as a constant, and so the derivative is 0. Let's take a look at another example. Let's let f of x and y equals to x cosine y plus secant of x times y. Okay. This function of x and y, without concerning ourselves too much about what the domain of the function is, we can simply find the partial derivatives. The partial with respect to x at a point x and y is going to be equals to what? Treating y as a constant, cosine y as a constant, so that this becomes the derivative of x, which is 1 times cosine y. Plus, now this is the composition, it's secant of xy. We're treating y as a constant, so the derivative, however, is going to be equal to secant xy tangent xy times the derivative of xy. Well, y is a constant here, so this is like the constant times x. Derivative of constant times x is going to be the constant. That's to say this is secant xy tangent xy. Y, the second part here. Partial with respect to y. Right? And xy. Treating x as a constant, this is x times the derivative of cosine y with respect to y, which is going to be minus sine y. So minus x sine of y. Plus, taking the partial with respect to y here, so we treat x as a constant. This is a composition, however. This is secant of xy. So the derivative is going to be secant xy tangent xy times the derivative of xy with respect to y, which is going to be x. that there are those partial derivatives given this function. Let's take a look at a third example. Let's say f of x and y is equals to y times logarithm of xy plus x squared. Right. The partial with respect to x. We treat y as a constant here, that this becomes, that this is equal to y times the derivative of this right here with respect to x, which is going to be 1 over xy plus x squared times the derivative of xy plus x squared with respect to x. X times y, the partial derivative is going to be y. X squared, differentiating with respect to x, we're going to get 2x. So there's the partial derivative of this with respect to x. The partials with respect to y. Now with respect to y, this is the product. So the partial derivative is going to be the first times the partial derivative of the second plus the second log of xy plus x squared times the partial derivative of y here, which is 1. So we need the partial derivative of the second here. We've got y. The partial derivative of this with respect to y is going to be 1 over xy plus x squared times the partial derivative here of this with respect to y, which is x. So there's that. Let's take a look at a function of 3 variables here. Let's let f of x, y, and z be equals to z e to the x cosine y plus x squared y cubed z to the 4th. Okay. The partial with respect to x at x, y, and z. Now here you treat y and z as if they're constants and just differentiate with respect to x. So we're going to get z, derivative of e to the x is e to the x cosine y. Cosine y is fixed, and as is z here. Plus, fixing y and z and differentiating with respect to x, we get 2x y cubed z to the 4th. The partial with respect to y at a point x, y, and z. Right. Here we fix z and x and differentiate with respect to y. So we get z e to the x. Derivative of cosine y with respect to y is going to be minus sine y. Plus x squared z to the 4th, the derivative of y cubed is going to be 3y squared. So we have 3x squared y squared z to the 4th. Partial with respect to z. And the point x, y, and z. Right. Treating x and y now as fixed, differentiating with respect to z here, we get e to the x cosine y plus x squared y cubed times the derivative of z to the 4th, which is times 4z cubed. Right. So it's clear here that if you've got functions that are algebraic or involve trig functions or logarithms or exponents in x and y, you can compute the partial derivatives using what you already know about ordinary derivatives. We're going to look at what are called higher partial derivatives here now. Just as with a function of one variable, you can take the derivative, and then if the derivative is a function, you can take the derivative of the derivative, getting the second derivative. Here you can take partial derivatives of the partial derivatives, assuming that they're functions. The notation for this is as follows. If we start with a function f, and we then get the partial of f with respect to x, or at x and y, or alternate notation that this is the partial of f with respect to x. We also get the partial of f with respect to y at x and y, or partial f with respect to y. Right? We take the partial of with respect to x and then do it again. You write fxx at x and y. This is to say this is the partial with respect to x of the partial of f with respect to x. This notation is rarely used, though. What's written is like this, as if you could multiply this out. The second partial of f with respect to x. But similarly, the partial with respect to y, then with respect to y at x and y is equals to the partial with respect to y of the partial of f with respect to y, which is written as second partial of f with respect to y. It's just as if you could multiply this out. The partial with respect to x and then with respect to y at x and y is written like this. This is with respect to x first and then with respect to y. I say this is the partial of f, the partial of, with respect to y, of the partial of f with respect to x. And this is written as the second partial of f with respect to x and then with respect to y. Right? So that this indicates you take the partial with respect to x and then you take it with respect to y, put an additional y on here. Here, it's treated like as if it's an operation or a composition, and so that this means with respect to x first, and then this means with respect to y. And similarly, you can get third partials and fourth partials and so forth here. The partial of f with respect to x and the partial, and then with respect to y, turns out to be, in most cases, in almost all cases for that matter, the same thing as what you get if you were to take the partial with respect to y first and then with respect to x. I'll say something about that in a minute. Let's take a look at an example here. Let's look at f of x and y equals to x squared y cubed plus sine x plus y. All right? This is f of x and y. Then the partial with respect to x and x and y is equals to 2x here, y cubed plus cosine x. Derivative of y with respect to x here when y is fixed is 0. Partial with respect to y at x and y is equals to 3y squared times x squared, or 3x squared y squared. Partial of this with respect to y is 0, so this is then plus 1. Right? The partial with respect to x and then with respect to x at x and y. Right? Take the partial with respect to x and take its partial derivative with respect to x. So this is going to be equal to 2y cubed minus sine x. Partial with respect to y, and then with respect to y at x and y. Take the partial with respect to y, take the partial of that with respect to y. We get that this is equal to 3 times 2 x squared y, or 6x squared y. The partial with respect to x, and then with respect to y at x and y, is equals to, take this partial with respect to x, now take the partial of it with respect to y, and we're going to get 2x times the partial of this with respect to y, that's going to be 3y squared, or altogether here, 6xy squared. Right? Now, suppose instead we took the partial with respect to y first, and then with respect to x at x and y. I just said that these should be equal, and if we take the partial with respect to y first, now we take the partial of this with respect to x, what do we get? Partial of this is 0, and we get 6x y squared. So these are equal here. So as a consequence of the fact that these are going to be equal, for most cases, I'll mention what the cases are in just a second, it doesn't matter which order you write these in. That's to say, fxy y is going to be the same as f y, x, y, and so forth here. Right? Why should these turn out to be equal? Well, let's take a look at what they are. The partial with respect to x is the limit as h approaches 0. Well, let me write it here. The limit as h approaches 0, f of x plus h and y minus f of x and y divided by h. Now suppose we wanted to take the partial of that with respect to x, and now we want to take the partial of it with respect to y. Well, we should do this at y plus k then. That's to say, take the limit as h approaches 0, f of x plus h and y plus k minus f of x and y plus k, and divide this by h, subtract these two, and divide the whole thing here by k. Take the limit as k approaches 0. This is going to be the partial with respect to x, then with respect to y at a point xy. Well, if we combine these two limits here, we find out that what we're looking at is the limit as h approaches 0, f of x plus h minus, and y plus k, minus f of x and y plus k, minus f of x plus h and y, minus f of x and y, this is plus now, because we have minus here. We combine these two limits, and this is divided, each of these is divided by h, and then divided by k, so we could divide them by h and then k, and now take the limit here as k approaches 0. This is going to be the partial with respect to x and then with respect to y. Providing that these limits exist here, right? Right? Now, suppose instead that we had computed we wanted to compute the partial with respect to y and then with respect to x at the point x and y. Well, it would be exactly the same as this. If you write this out in the same manner here, you're going to get exactly the same quantity inside here. The only difference that you're going to get is that you're going to have the limit with h going to 0 on the outside and the limit of k going to 0 on the inside. So, to compute this, you make this substitution and compute the limits. Well, if it doesn't make any difference whether you let h go to 0 first and then let k go to 0 or vice versa, then you're going to get the same result in the limits. And now, if the partial derivatives with respect to x are continuous, then and you've got a second partial here, then it doesn't make any difference, it turns out. And so consequently, taking the partial with respect to x and then with respect to y results in the same thing as taking the partial with respect to y first and then with respect to x, providing you end up with continuous function here, or providing that the partials themselves with respect to x or with respect to y are continuous. This fact is called the equality of mixed partials. The fact that the partial with respect to one variable and then with respect to another is the same as if you would, when you interchange the variables, is called the equality of mixed partials. So here are some examples of the higher partials here for a particular function, and this shows, here's the notation, and this shows why the mixed partials are equal. functions of three variables, story is similar here. So if we start out with a function x, y, z, right, then the partials are denoted by partial with respect to x at x, y, z. Sometimes the x, y, z is deleted here, so that you denote this by the partial with respect to y and the partial with respect to z. The second partials then, fxx, fyy, and fzz. And there are the mixed partials, fxy, and this, as for functions of two variables, is going to be equals to fyx. You've also got fxz, which is going to be the same as fzx, as long as we've got continuity, for example, and fyz, which is going to be fzy. Right? And then you can compute also the third partials, fxx, for example, fxxx, fyyyy, yyyy, fzzz, fx, y, for example, and you've also got such things as fxyz. All right, all of the possible combinations here of x, y, and z for the third partials, with again, for example, fxyz is equals to fyxz, and other arrangements are equal also here. So this is also equal to fzyx, right, provided we've got continuity. Let's take a look at an example. Let's let f of x, y, z here be equals to, I'll say x cubed, y to the fourth, z to the fifth, plus log of x plus z plus e to the y. Then the partial with respect to x, right, is going to be equals to 3x squared, y to the fourth, z to the fifth. Treating y and z as constants here, plus derivative of logarithm is 1 over x plus z. And as the derivative of this with respect to x, the partial, all right, is going to be 1. This is 1. Partial with respect to x of z is 0. Partial with respect to x of e to the y is 0. So that's the partial with respect to x. The partial with respect to y, this is going to be 4y cubed here. So 4x cubed, y cubed, z to the fifth, plus, there's no y term in here, so the partial is going to be 0. The partial of e to the y with respect to y is e to the y. Partial with respect to z. Okay, treating x and y as constants, differentiating with respect to z here, we get 5z to the fourth, or 5x cubed, y to the fourth, z to the fourth, plus, this has a z in it, so it's going to be 1 over x plus z times the derivative of x plus z, which is 1. With respect to z, the derivative of x is 0, the derivative of z is 1. Partial derivative of e to the y with respect to z is 0. Partial with respect to x, and then with respect to x. If the partial is with respect to x, we're going to get 6x, y to the fourth, z to the fifth, plus, this is x plus z to the minus 1, so we're going to get minus 1, x plus z to the minus 2, times the partial of this with respect to x, which is 1, right? Partial with respect to y, and then with respect to y, is partial of this with respect to y. We're going to get 3y squared here, so altogether 12x cubed y squared z to the fifth, plus partial with respect to y is e to the y. Partial with respect to z, and then with respect to z. Take the partial of this with respect to z, so we're going to get 20 x cubed, y to the fourth, z cubed, plus, this is 1 over x plus z minus 1, so we're going to get minus 1 x plus z to the minus 2 times the partial of this with respect to z, which is 1. Huh? Partial with respect to x, and then with respect to z, for example. Here's the partial with respect to x. We take the partial of this with respect to z. We're going to get 15. We're going to get 5z to the fourth here, so this is going to be 15 x squared y to the fourth z to the fourth. Now take the partial of this with respect to z. This is 1 over 1 plus z, or 1 plus z to, 1 over x plus z, or x plus z to the minus 1. So the partial derivative is going to be minus 1 x plus z to the minus 2 times the partial of this with respect to z, which is 1. All right? Let's check to make sure that this is also the partial with respect to z first, and then with respect to x. Here's the partial with respect to z. We take the partial with respect to x, we get 3x squared, so altogether 15x squared y to the fourth to z to the fourth. That's right. The partial of this with respect to x now is minus 1 x plus z to the minus 2 times the partial of x plus z with respect to x, which is 1. So that this is equal to the partial with respect to z and then with respect to x. Okay, so here's an example of a function of x, y, and z and various partial derivatives of it. And this, of course, is the notation that's used for those. The interpretation of the derivative for a function of a real variable is that it is the slope of the tangent line to the graph. And for functions of two variables, you would expect if the function is smooth enough, then instead of a tangent line to the graph, you're going to have a tangent plane to the graph. And partial derivatives can be used to compute the equation for the tangent plane. So let's imagine that we've got some sort of function of x and y here. And we're interested in a point x naught, y naught, right? And hopefully this graph is smooth enough so that there's a plane that is tangent to f of x and y. In particular, this will occur if the function f of x and y has got continuous partial derivatives. That's to say, the values along the graph of f of x and y will approach a direction which lies in the tangent plane. Okay. We want to see how to get these, and so let's consider these two directions here. And let's first of all consider fixing y naught. So we look at this line in the xy plane to the point x naught, y naught, and 0, y naught. Right? And that's going to result in some sort of a curve, right, above it on the graph. Right? If we consider this direction right here of the curve, this particular vector in the direction of the curve ought to lie in the tangent plane. Well, what does it look like? What it looks like is this. If we go over in the x direction this amount, let's say 1 unit, right? This vector right here ought to be, we have to go up in this direction, the partial with respect to y at x naught, y naught. That's to say, this vector right here ought to be the vector I plus the partial with respect to x at x naught, y naught times times k. This ought to be this vector right here. we now do a similar analysis here, proceeding in this direction, right, we end up with a vector over here. And what should that vector be? Well, it wants to be j plus the partial of f with respect to y at the point x naught, y naught, times k. That's to say, if we proceed 1 unit over in the j direction here, the vector should go up or down according to what partial with respect to y at x naught, y naught is. So these are two vectors that should lie in the tangent plane. So that consequently, if we take these two vectors and take their cross product, this is going to give us a vector which is normal to the tangent plane. Once we have a normal vector, and we also know that the position of this is, it's at the point x naught, y naught, z naught, if you want, where z naught is f of x naught and y naught, then we'll be able to write the equation in the tangent plane. Okay, what does this cross product look like? Well, I crossed with k, right, is minus j, so it's minus the partial with respect to y at x naught, y naught times j. Okay. K crossed with j is minus I. So this is the partial of f with respect to x at x naught, y naught times I. Right? Finally, what have we got here? K crossed with k is 0. I crossed with j is k, so this is going to be plus k. So this vector right here then is going to be a normal vector to the plane. So what does that mean? Well, it means that a point x, y, z gets to be on this plane if x, y, z minus x naught, y naught, z naught dotted with the normal vector is equal to 0. That's to say, if we take any other point x, y, z on here and look at this vector like so, it ought to be perpendicular to the normal vector. Okay, what is this? This is x minus x naught times the partial of f with respect to x, and I'll just write partial f with respect to x here, all right, and x naught, y naught, well, let's write it in, and that's minus the partial of f with respect to y at x naught, y naught times y minus y naught, right? And then plus z minus z naught times 1. This must be equal to 0. Now, this is usually written by bringing both of these to the right-hand side here and writing that z minus z naught is equals to partial with respect to x at x naught and y naught times x minus x naught plus the partial with respect to y at the point x naught, y naught times y minus y naught. Thing to note here is that x naught and y naught are fixed numbers here, so this is actually an equation of a plane. That's to say, it's got a z term, a constant here. It's got this constant times x, another constant, constant times y, another constant. Second thing to note is this, that if we let x equal x naught and y equal y naught, and here we find out that z is equal to z naught, so that the point x naught, y naught, z naught is definitely on this plane. And secondly here now, since all these quantities here are constants, we consider this z equals to z naught plus this, then this is a function, z is a function here, and if we pick the partial derivative of it with respect to x, this part is 0 as is this, and here what we get is 1 times the partial with respect to x at x naught y naught, so the partial of z with respect to x is the partial of f with respect to x at the point x naught y naught. Likewise, the partial z with respect to y is the partial of f with respect to y. This and this produces 0 when you take the partial with respect to y. This produces a 1, so this is the partial with respect to y at x dot y dot. So that this is the equation of the plane that lies, that goes through this point, x naught, y naught, z naught, and which has for its partial derivatives the same partial derivatives that f does. Right? Now, this formula here in this form is fairly memorable. That's to say, it's worth remembering that this is how to do this. Note the analogy to functions of one variable. If we were looking at a function of one variable, then we would have that y is equals to f at x naught plus f prime at x naught times x minus x naught. This is the equation of the tangent line. We're looking at a function f of x which is differentiable at x naught. Well, here this is z is equals to f of x naught y naught plus the partial times x minus x naught plus the partial times y minus y naught. We've looked at the higher partials, and well, usually no one goes into great detail in a calculus class about applications of the higher partials. There is an analogous application to that of Taylor series for the derivatives of a function. That's to say, here we've written the function, an approximation to the function using the tangent line, namely z is z naught plus this partial times x minus x naught plus the partial times y minus y naught. Right? We can also write something that looks like this. P of x and y equals to z naught plus the partial with respect to x at x naught y naught times x minus x naught plus the partial with respect to y at x naught y naught, I'm leaving that out, times y minus y naught. Here we've got the tangent plane, but now we can continue this with the partial with respect to x and then with respect to x at x naught y naught times x minus x naught squared over 2 factorial plus the partial with respect to y and then with respect to y times y minus y naught squared over 2 factorial, right? Plus the partial with respect to x and then with respect to y times x minus x naught times y minus y naught, right, over 1 factorial times 1 factorial. Right? And you can continue on in this fashion, producing a polynomial in x and y that has the same value at the point as the given function. It has the same partial derivatives. It has the same mixed partial derivatives. Right? And it has the same partial derivatives as high in order as you want. And this frequently is a good approximation to the function at points specifically near x dot y dot, and sometimes for points that are further away. So there's an analog to Taylor series here, which uses the higher partials, although we're not going to use them to any great extent, anything higher than the second order partials. Let's take a look at some specific examples of finding the equation of tangent point at a specified point. Let's let f of x and y equals 2x squared plus y squared. Right? This is a easily graphed function. It's a paraboloid. And when y equal to 0, we're looking at z is 2x squared. So that's going to be like so. And when x is equal to 0, we're looking at z is equal to y squared. So that's going to be like this. And the resultant parabola looks something like this. Right? Let's look at the tangent line at the point, let's say 3, 4. Right? Here's f of x and y. F of 3, 4 is 2 times 9 plus 16, or 18 and 16 is 34. So this is up there. And you'd expect the tangent plane to be a little bit on the steep side also. Here, let's look at the partial with respect to x. At x and y, this is equal to 4x. So the partial with respect to x at 3, 4 is equal to 12. Well, we'll put 3 in here for x. Partial with respect to y at x and y is 2y, so the partial with respect to y at 3, 4 is equal to 8. Okay, so consequently the equation of tangent plane is going to be z is equal to 34 plus the partial with respect to x, right, at the point, which is 12, times x minus, our point here was 3, 4, so it's going to be x minus 3, plus the partial with respect to y at the point is 8. The point was 3, 4, so this is going to be times y minus 4. It's clearly the equation of a plane. Right? The value when x is 3 and y is 4 is 34. If you take the partial derivative with respect to x of this plane, we get 12. Right? This producing 0 and this producing 1 and this 0. So we get 12. And the partial with respect to y of this function z here gives us 8. And so it's a plane with the same partial derivative and with respect to x and with respect to y and the same value as the function at this point. All right. Let's take a look at one that's not so easy to graph, but it really doesn't matter. That's to say, at this point you can do just about anything, providing you know your basic calculus 1 methods for taking derivatives. So let's let f of x and y be equals to x cubed y plus e to the x plus sine y. And let's look at the point 1 pi over 2 here. F at 1 and pi over 2. This is going to be 1 cubed times pi over 2 plus e to the 1 plus the sine of pi over 2, which is 1. Right? The partial with respect to x of this at x and y is going to be equal to 3x squared y plus e to the x. The partial with respect to x at 1 pi over 2 is going to be 3 pi over 2 3 times 1 times pi over 2 plus e. The partial with respect to y at x and y is going to be x cubed plus cosine y. So the partial with respect to y at 1 pi over 2 is going to be 1. Cosine of pi over 2 is 0, so it's going to be 1. The equation of the tangent plane consequently is going to be z is equals to the value of the function, pi over 2 plus e plus 1, plus the partial with respect to x, 3 pi over 2 plus e times x minus 1, the x dot value, plus the partial with respect to y, which is 1, times y minus pi over 2. So here's the function of x and y, which is not particularly simple. Here's the equation of the tangent point at this point right here. The next topic we want to look at are differentials. So these are the analogs to differentials for functions of one variable. If we've got a point, fixed point x naught, y naught, we wish to vary from this point by a quantity delta x and delta y to arrive at the point x naught plus delta x, y naught plus delta y, then we write delta f. Right? This is the change in f, or it's also called the increment. Right? To be equals to f of x naught plus delta x, y naught plus delta y minus f of x naught y naught. Right? The thing to note about this quantity is that it depends on 4 things: x naught, y naught, delta x, and delta y. Right? It's the actual change between the value of the function at x naught, y naught, and the function at x naught plus delta x, y naught plus delta y. Right? However, frequently what you want, instead of the increment, is to use an approximation for it, which is called a differential. Right? Now, the differential at this point in time is perhaps more frequently used for theoretical reasons rather than for practical ones, because of the calculators and computers today, which can compute things to very large accuracy. However, the differential is written as df, right? And it's defined to be the partial of f with respect to x at x naught, y naught times delta x plus the partial of f with respect to y at x naught, y naught times delta y. Right? And note again that for the differential depends on 4 quantities: x naught, y naught, delta x, and delta y. Now, this is used for 2 purposes frequently. One of them is this: the delta f is approximately the same as df. Right? So if you want to compute the change in f, you can usually approximate this by df. In fact, it is equals to it in the limit. In fact, the limits as delta x and delta y go to 0, these tend to be very close approximations to each other. Right? The differential of f is the change on the tangent plane to the graph of f. So you can expect that the change on the tangent plane is going to be very close to the actual change in f. This is the analog of the differential function of real variables, a function of a single variable, where the differential is the change on the tangent line as compared to the change of the function. So this is used for this purpose right here, namely that delta f is approximately equals to df. It's also sometimes used for the following fact, that f of x naught plus delta x, y naught plus delta y is approximately equals to f of x at x naught and y naught plus df. Right? This is really the same type of approximation. This minus this is approximately df. These are two ways in which the differential is used. Right? And also there are differentials for functions of three variables. So that if we've got f of x, y, and z, right? And now if we've got a point, x naught, y naught, z naught, we also have changes here, delta x, delta y, and delta z given. Then the differential of f is going to be equals to the partial of f with respect to x at x naught, y naught, z naught, delta x, plus the partial of f with respect to y at x dot, y dot, z dot, times delta y, plus the partial with respect to z at x dot, y dot, z dot, times delta z. And here you can note that this differential depends on six quantities: x dot, y dot, z dot, delta x, delta y, and delta z. Let's take a look at a simple example here of how the approximation of the differential to the actual change or the increment in the function. Let's suppose that we wish to compute, let's say, the square root of 3.02 squared plus 3.9 squared. Right? If we let the function f of x and y be equals to square root of x squared plus y squared, right? Now, if we also let x naught be equal to 3 and y naught be equal to 4, right? If we were to put 3 squared plus 4 squared here, you'd expect that the approximation would be pretty close. How far off would it be? Right? Well, we're going to let delta x be 0.02 and delta y be minus 0.1. Right? Then this is equals to f of x naught plus delta x, y naught plus delta y. That's this quantity right here. Right? And now we know that f of x naught plus delta x, y naught plus delta y is approximately equals to the square root of 3 squared plus 4 squared, the value at x naught, y naught, plus df. Well, for df, we need the partial of f with respect to x. This is 1/2 x squared plus y squared to the minus 1/2. So 1/2 of this times 2x. So the half's going to cancel and we'll end up with x here. The partial of f with respect to y is equal to y over the square root of x squared plus y squared. At the point we're interested in, and the point was chosen for ease in calculations here, 3 squared plus 4 squared is 5 squared, so that we end up with this is equal to 3/5 at the point we're interested in, and that this is equals to 4/5 at the point we're interested in, so that the value of this number right here is approximately equals to square root of 3 squared plus 4 squared is 5, plus the partial with respect to y is, with respect to x is 3/5, and now times delta x, which is 0.02, plus the partial with respect to y, which is 4/5, times delta y, which is minus 0.1. Right? So that this is equals to, let's say 6/10 times this is going to be 0.018 2, and 8/10 times this is going to be minus 0.08 and 5. Right? Which is, what, 4.92? 4.932. That's an approximate value of this, and it should be pretty accurate because this is, the changes here are delta x and delta y are reasonably small. All right, so here's the differential. It actually has got a couple of uses. One is for approximating the change in f, and the other one is for approximating a new value of f. And here's an example of such a calculation. We're going to need some notion as to how accurately the differential approximates the value of the function, or the change in the value of the function. And so let's recall here that delta f, if we're given a point, I'm drawing this in the xy plane here now. We're given a point x naught, y naught, and another point x naught plus delta x, y naught plus delta y. Right. Then delta f, right, is equals to f of x naught plus delta x, y naught plus delta y, minus f of x naught and y naught. This is the change in, the actual change in f. Now I want to complete this triangle here so that this third point, for example, as I've drawn it, is the point x naught, y naught plus delta y. I'm sorry, it's the point x naught plus delta x, y naught. It's got the same x value as this point above it here, and the same y value as the point to the left of it. Okay. What I want to do now is I want to rewrite this as what I get if I subtract this point and then add it back on here. So this is going to be f of x naught plus delta x, y naught plus delta y, minus f of x naught plus delta x, y naught, right, plus f of x naught plus delta x, y naught, minus f of x naught and y naught. So that's equal to this, like so. And now, what I wanted to use is the mean value theorem for derivatives. Recall that if you've got a differentiable function defined on an interval a, b, right, then if I look at f of b minus f of a over b minus a, this is equal to the derivative of f at some point z, where z is in the interval from a to b. Right? Or, if you like, f of b minus f of a is equal to the derivative at z times b minus a. I want to use this type of thing here now, except for partial derivatives. And what that means is this. This difference right here, right, is the difference between the value of the function at this point and the value at this point right here. So it's going to be equals to the partial derivative with respect to x at some point in between here times delta x. So it's going to be equal to the partial with respect to x at, let's say, x naught plus delta 1 y naught times delta x. Right? This difference is going to be the derivative times the length of the interval. This one right here goes up this interval like so. Right? So there's going to be some point in between here on this interval, so that we can write this as the partial with respect to y at that point. Right? That's to say at x naught plus delta x, y naught plus some delta 2 here. Delta y. So if delta 1 and delta 2 are chosen properly here, we're going to get equality here with the increment, delta f. Now, if f with respect to x and f with respect to y are continuous, then we can replace this with the value at x naught plus some small change which goes to 0. So we're going to do this. We're going to write this as the partial with respect to x at x naught, y naught, delta x, plus some epsilon 1, which depends on delta x and delta y, so that this times delta x, right? This plus this is this quantity right here, so we have delta x multiplying both of them. And epsilon 1 goes to 0 as delta x goes to 0. This quantity right here can be written as the partial with respect to y. Instead of this point, we're going to look at this at the point x naught, y naught, right? Delta y. And now we're going to have another error term here, a second epsilon, epsilon 2, which depends on delta x and delta y, times delta y. That's to say, this differs from this by this epsilon 2, and if we've got continuity of fx and fy, then these will go to 0 as delta x and delta y approach 0. So we're assuming continuity of fx and fy. All right, now, but what is this? This is df, right, plus epsilon 1 delta x plus epsilon 2 delta y. Well, epsilon 1 and epsilon 2 depend on these two, but they go to 0 as delta x and delta y approach 0. Or as delta x, delta y approaches the point 0, 0. So what this says is that df is a good approximation for delta f in the following sense. That it differs by it, not just by something which goes to 0, because as delta x and delta y go to 0, this would go to 0, but something which goes to 0 when you multiply the first quantity by delta x and the second by delta y, right? The quantities that multiply delta x and delta y themselves go to 0 as delta x and delta y approach 0. So we're going to need this situation right here from a theoretical standpoint, namely that the differential is this good of an approximation of delta f. We now want to take a look at the chain rule for functions of several variables. We're going to take a look at the simplest cases. The other cases are exactly analogous to this. That's to say, let's suppose that we've got a function f of x and y. And now y is also a function, and so is x. That's to say, y is a function of t, and x is a function of t. X is x of t. And so consequently what this does is this defines implicitly the function f of t. All right? Now, what we want to do is we want to use the differentials to get at the derivative of f of t. Recall that f of x plus delta x, y plus delta y, minus f of x and y is equals to partial of f with respect to x at x and y delta x plus partial of f with respect to y at x and y delta y plus epsilon 1 of delta x and delta y delta x plus epsilon 2 of delta x and delta y, where these two go to 0 as delta x and delta y approach 0. Now, we've got this function f of t defined by this composition here, and we want to take a look at the derivative. We're assuming that the function f has got partial derivatives here like so, and that the function y is differentiable and the function x is differentiable. So the derivative at a point t is going to be equal to the limit as delta t approaches 0 of f of x of t plus delta t, y of t plus delta t, that's the value of the function f at t plus delta t, minus f of y of t, of x of t, y of t, divided by delta t. That's the definition of the derivative. Okay. Now, what we want to do is we want to use this fact right here, where x of t plus delta t minus x of t is delta x. So we're going to let delta x equal x of t plus delta t minus x of t. We're going to let delta y be equals to y of t plus delta t minus y of t. All right? Then this becomes equals to the partial with respect to, this becomes equal to the partial with respect to x of the partial with respect to x at x of t, y of t times delta x, which is x of t plus delta t minus x of t. Right? That's this first part. Plus the partial with respect to y at x of t, y of t, times y of t plus delta t minus y of t, plus, in this first case here, we have epsilon 1 times delta x, and in the second case, we've also got plus epsilon 2 times delta x. So that's the numerator here, and now we need to divide the whole thing by delta t. So over delta t and over delta t. Now, we want the limit on this as delta t approaches 0. Well, this is a fixed quantity right here, and so is this. And the limit as delta t approaches 0 of this quantity right over here is the derivative of x with respect to t. So what we get here is that this is the partial of f with respect to x times the derivative of x with respect to t.